Hey, we learned about partial fractions the other day. Let's do some examples. I'll do the first one real fast just to remind us what's going on. The first step is to take this rational expression and to figure out how to rewrite it. And the first step in rewriting it is factoring the denominator. And since we have two linear factors, x plus 2 and x plus 3, the structure of the partial fractions decomposition is some number that I'll call a over x plus 2 plus some other number b over x plus 3. I get asked this a lot. Does it matter which one you call a and b? Of course it doesn't. You swap them around, and if you called the thing over x plus 2 b, then great. Whatever we get for b will be over x plus 2. Whether you called it a or b or whatever, you'll get the same answer in the end. And now the trick is to make progress from here. We'd like to clear the denominators. So what we do is multiply both sides of this equation right here by x plus 2 times x plus 3. And I strongly recommend really writing this step out and doing it carefully. You'll start to see a pattern, but it won't always work. It will certainly here. That's why you'll see a pattern, because it will work some of the times. But when they get a little bit more confusing, it won't. So if you do the algebra carefully, then you'll come up with the right answer. And what happens here is that on the left, the denominator x plus 2 times x plus 3 cancels with the x plus 2 times x plus 3, and we're just left with 1 minus x. And on the right, we have to distribute. And x plus 2 times x plus 3 times a over x plus 2. The x plus 2's cancel, and you get a times x plus 3. And similarly, when you multiply x plus 2 times x plus 3 times b over x plus 3, the x plus 3's cancel, and you get b times x plus 2. And now we have to find the values of a and b. There's more than one way to do it, but for this problem, the easiest way is probably to use the method where you say, well, this equation has to hold true for any possible value of x, and so I can choose some interesting values of x to try to make it easy. For example, when x equals negative 3, we get 1 minus negative 3, or 1 plus 3 on the left, and then a times negative 3 plus 3, which is why I picked x equal to negative 3, because negative 3 plus 3 is 0, and that term will go away, and then a b times negative 3 plus 2. And that gives us that 4 is equal to negative b, so b is negative 4. Similarly, if we choose x equal to negative 2, and when you plug negative 2 in for x, you just get 3 equals a. 1 minus negative 2 is 3, and then you get a times negative 2 plus 3, which is 1, so that's 1 times a, and negative 2 plus 2 is 0, and 0 times b is 0, so that term goes away, and so we just get a is equal to 3. So now we know that a is 3, and b is negative 4. And that tells us that the original expression that we were looking at over here, well, we know that that's supposed to be equal to this expression right here, and so we get that 1 minus x over x squared plus 5x plus 6 is really 3 over x plus 2 minus 4 over x plus 3. And now we're ready to integrate. All we've done so far is algebra, but now we know a new algebraic expression for the thing we're trying to integrate. It's easy to integrate. We should break it into two integrals. We should do each of them by substitution. In the first, you let r be x plus 2. In the second, let u or s be x plus 3. Don't really want to choose r twice. And I'll let you verify that we get this answer right here. Be careful with the substitution in the future. It won't always work out quite so simply. So do it slowly and carefully and make sure you get the right answer. Okay, that was me burning through one just to show you how it's done and get you warmed up. Your turn. Okay, you try this one. Yes, I realize that the denominator is harder to factor than the one that I gave myself. Sorry about that. But you can do it, promise you. Take a few minutes, work out the partial fractions decomposition, and then compute the integral. It'll take you a few minutes, don't rush. Pause the video. When you're ready, start it back up again. The denominator factors is 3x plus 5 times x minus 1. Those are two linear factors, just like in the last example. And so the expression we're looking for can be written as a over 3x plus 5 plus b over x minus 1. We multiply both sides by 3x plus 5 times x minus 1. And after we distribute and simplify, we get this expression here. Once again, it will be easier to just pick values for x that make this easy. In particular, a good choice is x equals 1. And when you plug that into the equation, you get negative 16 equals 8b. After the term with the a in it goes away because 1 minus 1 is 0. And so b is equal to negative 2. I suppose we could pick x to be equal to negative 3/5 to do the same thing and make the b term go away and solve for a. But it's not necessary. We already know what b is equal to. We don't need that term to go away. We could pick any value for x, and we may as well pick a value that makes the computation easy. So let's see what happens at x equals 0. Plugging in x equals 0, we get a negative 14 on the left, and then we get a times 0 minus 1, that's a times negative 1. And then 3 times 0 is 0, so we get 5b, and b is negative 2, so that's where that 5 times negative 2 comes from. And simplifying, we get that negative 4 is equal to negative a, or a is equal to 4. This tells us that our original expression is equal to 4 over 3x plus 5 minus 2 over x minus 1. So that's what we were trying to figure out. So all we've done so far is a bunch of algebra. Now it's time to integrate. As before, we can split it into two integrals. They're both substitution problems. The one on the left is more interesting. You have to let r be 3x plus 5. So dr is 3x dx. I don't have a 3x dx. So you have to divide both sides by 3 to get that dx is 1/3 dr. And on the right, picking a new variable, I'll let u be x minus 1. So du is just dx, and that's a little bit simpler. We can pull the constants, the 4 in the numerator and the 2 in the numerator, outside of the integrals, and we can rewrite these integrals in terms of the new variables. And we get this expression here, where in particular on the left, the dx became a 1/3 dr. And the integral of 1 over r is the natural log of the absolute value of r, just like the integral of 1 over u is the natural log of the absolute value of u, giving us our final answer of 4/3 the natural log of the absolute value of 3x plus 5 minus twice the natural log of the absolute value of x minus 1 plus a constant. Okay, this one's more fun. I'm going to give you a number of opportunities to pause and restart the video on this one, just because I don't want you going down the wrong path for too long. So start by factoring the denominator and seeing if you can set up the appropriate structure of the partial fractions decomposition. Pause the video. Once you have the structure of the partial fractions decomposition set up, the a over something, etc., then stop and make sure you've got it right, and then we'll continue on together. X squared minus 6x plus 9 factors as x minus 3 times x minus 3, which is x minus 3 squared. And so the structure of the partial fractions decomposition is some number a over x minus 3 plus some number b over x minus 3 squared. I see a lot of people who want to put an ax plus b or a bx plus c or something like that in this. Nope, there is no irreducible quadratic here. The x minus 3 squared is a linear term squared, not the same thing at all. Okay, the next step is to try to compute a and b. Why don't you take a few moments and see if you can do that. Pause the video, do it slowly and carefully, come up with the right answer, and then when you have a and b computed, stop and we will reconvene and make sure that we are on the same track. The idea, as always, is to multiply both sides of the equation by the denominator x minus 3 squared. That will make the denominators all go away. But the idea also, as always, is to do it carefully and correctly. In particular, on the left, x minus 3 squareds cancel, the one in the numerator and the one that you're multiplying by, and you just get x. And on the right, after you distribute, x minus 3 squared times a over x minus 3, well, one of the x minus 3's cancel, and you're left with a times x minus 3. And then b over x minus 3 squared times x minus 3 squared, the x minus 3 squareds cancel, and you're just left with b. And so here's where I was warning you about people who see patterns in magic and just think they're going to jump in on the answer without actually doing the algebra, tend to get this step wrong. And they write something like a times x minus 3 squared plus b times x minus 3. Nope, it does not work that way. Do the algebra carefully. This is what you come up with, and this is what will allow us to solve for A and B correctly. And as is so often the case, the easiest way is to start by choosing a particular value of x, and in this case, the particular value x equals 3 is attractive, because plugging in x equals 3 immediately gives us 3 is equal to b. To find a, we can now use any value of x that makes the arithmetic easy. X equals 0 is probably a good choice. X equals 1 are probably a good choice. I'm going to pick x equals 4 because I like what it does to that term that you're multiplying a by. 4 minus 3 is 1, and so we'll just get a 1a there. And so plugging in x equals 4 and b equals 3, we just get that 4 is equal to a plus 3, and so a is equal to 1. What we've just determined is that x over x squared minus 6x plus 9 is equal to 1 over x minus 3 plus 3 over x minus 3 squared, and we can use that to do the integral that we started with. So take a few moments and see if you can't integrate this expression here. So see what you can do when you're ready. So pause the video now. When you're ready to check your work, start it up again, and we'll make sure we got the same answer. It's a substitution problem. You could split it into two integrals, but it turns out that you don't really have to because it's the same substitution for both integrals. R equals x minus 3, and so dr is just equal to dx. This gives us the integral of 1 over r plus 3 over r squared. And in order to integrate 3 over r squared, it helps to write it as 3r to the negative 2. Because the integral of r to the negative 2 is r to the negative 1 all over negative 1. So simplifying this and rewriting it in terms of x gives us our answer, the natural log of the absolute value of x minus 3 over x minus 3 plus a constant. Okay, try one more. I believe you have one very much like this on your homework. Factor the denominator and give the structure of the partial fractions decomposition, and then start the video back up to make sure that you're on the right track before you finish. I wouldn't want you to spend too much time going down the wrong path. So take a moment, see if you can factor the denominator and come up with the structure of the partial fractions decomposition, and then we'll check in. X to the fourth minus 1 is the difference of two squares. It's x squared plus 1 times x squared minus 1. X squared plus 1 is an irreducible quadratic. You can't factor that any farther over the real numbers. But x squared minus 1 is not. It factors into x plus 1 times x minus 1. And so the full factorization of x to the fourth minus 1 is x squared plus 1 times x plus 1 times x minus 1. And so each of those factors gets some component of the partial fractions decomposition. And in particular, we get an ax plus b, a linear term, over the x squared plus 1, plus a c over x plus 1, and a d over x minus 1. And if the letters were mixed around or you move those factors around, it doesn't really matter. It'd be the same thing in the end. What I call a, you might call d, but we ought to get the same expression for what 1 over x to the fourth minus 1 is equal to. All right, take a few moments, see if you can solve for A, B, C, and D. Pause the video. When you're ready, start it back up. As usual, we multiply both sides by the denominator, which in this case is x squared plus 1 times x plus 1 times x minus 1. And as usual, we have to be careful about how we do it and what cancels. On the left, we just get a 1. On the right, the x squared plus 1 cancels with the x squared plus 1 in the denominator of the ax plus b, and then c over x plus 1 times x squared plus 1 times x plus 1 times x minus 1. The x plus 1's cancel, and we're left with c times x squared plus 1 times x minus 1, and similarly, the last term is d times x squared plus 1 times x plus 1. There are some good choices for x that will make this easy to figure out. In particular, you'll notice that when I let x equal 1, this term becomes 0 and this term becomes 0, so that this whole term goes away and this whole term goes away. And I'm just left with 1 equals d times 1 squared plus 1 times 1 plus 1, or d times 4. So d is equal to 1/4. Similarly, if I let x be -1, then this becomes 0 and this becomes 0. So this term goes away and this term goes away. And we find that c is equal to -1/4. X equals 0 is also useful because it will make the a go away, and so then we'll have something that just has a b in it, and we ought to be able to figure out what b is equal to. And using what we have already figured out about c and d, we get this expression. And after you simplify, you find that b is equal to -1/2. All that's left is to find a. We can use any value of x. We may as well pick something that makes the arithmetic easy. And although x equals 2 might seem like the logical choice, it turns out that the fractions are nastier that way. Trial and error. X equals 3 works out nicer. And after you work out the arithmetic, you find that a is equal to 0. Which lets us rewrite our original integral, the integral of 1 over x to the 4th minus 1, as the integral of -1/2 over x squared plus 1 minus 1/4 over x plus 1 plus 1/4 over x minus 1. You could break it into 3 integrals and pull those constants out if you like. You can do the x plus 1 and x minus 1, the second 2 parts, by substitution if you like. In the end, you get -1/2 the arctangent of x minus 1/4 the natural log of the absolute value of x plus 1 plus 1/4 the natural log of the absolute value of x minus 1 plus a constant. Okay, that was some superb practice doing partial fraction decompositions. You should be in excellent shape for your homework. Have lots of fun with it. See you in class. Bye.